Chapter 4 review. Example 1. Evaluate the Riemann sum. For f of x equals x squared minus x, and x is between 0 and 2. Do that with 4 subintervals, taking the sample points to be the right endpoints. With the right endpoints. And so we're going to show the graph. F of x is x squared minus x, factor out x, and here's the graph. The x-intercepts are 0 and 1, so 0 and 1. This is the graph. And we're interested from 0 to 2. So this is 1. Let's say this is 2. Okay, so we're talking about this region here. Let's write the interval from 0 to 2. If we have 4 subintervals, then n equals 4, divide by 1, divide by half here, 1/2, and 3/4. Okay, so here is 1/2, 1 and 3/4. All right, so we need to evaluate this Riemann sum. We'll call it R4, and that is sigma of f of xi delta x, and i's from 1 to 4, and delta x is, how do we find delta x? So we divide the length 2 minus 0 divided by 4, so it's 1/2. So let's expand that. We're gonna have delta x 1/2, and I can factor it out because it's 1/2 for each one of the rectangles. In fact, we can draw the rectangles with the right end. So here's one. Here's the other one would be here and here. Okay, so this one is down here. Okay, so I have f of 1/2. If we have the right end, that's going to be, this is going to be the height 1/2, plus f of 1, plus f of 3/4, plus f of 2. So these are the heights of the rectangles, f of 1/2, f of 1, those are the heights. So evaluate this, use a calculator, and you should get 1.25. And this is the estimation using n equals 4. All right, another example. Express the limit of sigma sine xi delta x. I is from 1 to n, and n goes to infinity. So express this limit of a Riemann sum as a definite integral on the interval from 0 to pi, and then evaluate. Okay, So let me write this limit again. And now we know that the limit of a Riemann sum is a definite integral. The interval is from 0 to pi. And the function, this is f of x. This is sine of x. And delta x is dx. So that's it. So to evaluate it, we want antiderivative of sine of x, which is negative cosine x from 0 to pi. That is cosine pi minus cosine 0. Cosine 0 is 1. Cosine of pi is negative 1. So it is exactly 2. All right, number 3. If integral of f of x dx from 0 to 6 is equal to 10, and integral from 0 to 4, f of x dx is 7, find integral from 4 to 6, f of x dx. So using the properties of integrals, definite integrals, I will write down the property so we can review it. Here's the property. If I have integral from a to c, f of x dx, plus integral c to b, f of x dx, that is equal to integral from a to b, f of x dx. And I'm going to illustrate this with a picture. So we have some function f of x, continuous from a to b, and c somewhere in the middle. So c is between a and b. So this property basically says that this area, which is the integral from a to c, plus this area, which is integral from c to b, is equal to the total area. So it makes sense. Let's go back to our problem. And in our problem, I have a equals to 0. That's the beginning of our interval. B is 6. And c, that's between them, is 4. So I can write down this property that from integral f of x dx from 0 to 4 plus integral from 4 to 6 is equal to integral from 0 to 6. And now we can substitute. What is given is 0 to 6 is 10. So this integral over here is 10. And what else is given? 0 to 4 is 7. This one here is 7. So what's left is that our integral from 4 to 6 should equal to 3, right? Okay, so next problem, number 4, evaluate. It has 3 parts. So A is integral from 0 to pi over 2 d dx, sine of x over 2, cosine x over 3 dx. So we're getting into fundamental theorem of calculus where we combine differentiation and integration. So we have to be careful what we do first. So first, we're doing differentiation and then integration. So we do that first. You do that first. And then integration, you do second, from inside out. So we know integration, differentiation are opposite, the inverse of each other, so they cancel each other. So that will be just sine of x over 2, cosine x over 3. Evaluate this from 0 to pi over 2. So when you differentiate first and then integrate, these two processes cancel each other. So we arrive at the original function f of x. And if you evaluate this, I'm just going to write the answer, root 6 over 4. You can easily do that at upper bound first and then lower bound. Part B is very similar but we're going to reverse the order now. So we're going to do integration first from 0 to pi over 2, same function, sine x over 2, cos sine x over 3 dx. And now, because we reversed the operations, we're going to do this first. And when you integrate definite integral, what do you get? This will be a number, right? Or a constant, because it's a definite integral. So what is the derivative of a number? And we don't care what that number is, because we're eventually going to get 0. We know the derivative of a number is 0. Okay, so part C, again, the same function, but we're going to change this. Instead of definite integral, we're going to make it from x to pi over 2. Same function, sine t over 2, cosine t over 3 dt. So the difference here between this part and part B is that upper bound, I should use a highlighter. The upper bound here is pi over 2. Actually, I wanted to point out that lower bound is x. It's not a number, so it's x. And so it's different from part B. So this is not going to be a number, it's going to be a function. So what I'm going to do, I'm going to reverse the boundaries and make it from pi over 2 to x. And we have a property that says if we do that, then we have a negative sign. And now this should be a familiar expression from the fundamental theorem of calculus, where it says if you integrate and then differentiate, then these two cancel each other, and they do, because here we have x for upper bound, so this is not a number anymore. So this is a function, and we arrive with the function in terms of x, so negative sine x over 2 cosine x over 3. And so we did this by the fundamental theorem of calculus, part 1. All right. So next problem, number 5. Find the derivative of the function. Find the derivative of the function. Let's do part A. The function is integral from 0 to x t squared over 1 plus t to the third dt. So we're using the same fundamental theorem of calculus to find the derivative of an integral. So that would be f prime of x, which would be d dx of this integral. So we said integration, differentiation are inverse processes, they cancel each other. So we arrive at the function, but I write it in terms of x. So our little f, I'll write it here, is x squared over 1 plus x to the third. And that's what this answer is here. All right. So part B of the same problem, find the derivative. Now my function big F is such that it's an integral from x to 1, square root of t plus sine of t dt. So a little different. We're starting with x, not with the constant, so we need to reverse it just like we did before. So I'm going to rewrite it as negative integral from 1 to x, square root of 1 plus sine of t dt. So you want the lower bound to be a number and the upper bound could be a variable. So to find f prime of x, that is d dx of our integral. So the rest will be the same. As we said, integration, differentiation, inverse processes. So that is keep the negative sign and write the function in terms of x. Okay, that's it. Okay, this was t, and I inadvertently wrote it as 1. So it is t, which make this x. And another part C. Now, a different function g of x is equal to integral from 0 to x to the 4th cosine t squared dt. So the problem here is that the upper bound is not just x, but a function of x. So we need to do change of variables. We're going to set u equals x to the 4th, and du dx is 4x to the 3rd. Now, we know that dg dx, the derivative of a function g, is equal to dg du times du dx. So we're going to go through u before we get to x. So to find the derivative of g prime of x, which is what we want to do, g prime of x, that is d dx of our function 0 to x to the 4th cosine t squared dt. But we have a problem. So the problem was that I have x to the 4th here and not just x. So we're going to go through u, and we're going to write this as d du first from 0 to u cosine t squared dt, and then times du dx. So now this part over here matches exactly our fundamental theorem of calculus part 1, where this u matches with this u. So we can cancel the integration differentiation. That is going to be cosine, but in terms of u. So that's very important. If you do here u, that's the function's going in terms of u. So cosine of u squared, and then I have du dx. Now go back and substitute. U was x to the 4th. So we have cosine x to the 4th, and then du dx is 4x to the 3rd. I like to write 4x to the 3rd on the front, so there's no temptations about simplifying further. Okay, so that concludes that problem 5 with finding the derivative. So number 6. A particle moves along a line with velocity function v of t equals t squared minus t, where v is measured in meters per second. So I'm going to put here meters per second. Find A, the displacement. Okay, or the difference of position of the particle from the beginning to the end, and B, the distance traveled by the particle during the interval from 0 to 5. Okay, so part A, to find the displacement, we have a formula. Displacement is equal to the difference of positions, s of t2 minus s of t1. This is supposed to be 1, and this is s. This difference in position is the integral from t1 to t2 of a function v of t. This displacement can be positive or negative. So we substitute. The time is from 0 to 5. So we have s of 5 minus s of 0 is equal to integral from 0 to 5. Function is t squared minus t dt. And now we have to evaluate this definite integral. So I'm going to do right away t to the 3rd over 3 is the antiderivative minus t squared over 2. And we're evaluating this from 0 to 5. Okay, so that should equal to 175 over 6, or approximately 29.16 meters. So that means the particle displays 29.16 meters to the right. If your displacement is positive, then it moves to the right. The total distance traveled is always a positive number. And our formula is almost the same, but now we have absolute value for the function because we want that to be positive. So in our case, it's integral from 0 to 5, and our function was t squared minus t dt. So how do we integrate the absolute value function? So we're going to do that right here. Our function is t squared minus t. I'm going to factor out t and see where does this function change its signs. At 0 and at 1, it's 0. And our interval is from 0 to 5, so that's all we need to know whether it's positive or negative in those intervals. So from 0 to 1, if you pick a number, let's say 1/2, plug it in here, 1/2 times 1/2 minus 1 is negative. And pick a number from 1 to 5, let's say 2. 2 times 2 minus 1 is positive. So what we found out that we can break our integral, so we are continuing here, break our integral from 0 to 5 as integral from 0 to 1, and then t squared minus t, that function here is negative. So we are going to put a negative sign in front of it, dt plus from 1 to 5, we saw that it's positive, so we can drop the absolute value and just t squared minus t dt. So let's evaluate this integral, and I'm just going to get it started. Negative t to the 3 over 3, and then that would be plus t, so plus t squared over 2, and then minus t to the 3 over 3. I should write my boundaries here first. I'm sorry. So this is from 0 to 1 for those two. And then here t to the 3rd over 3 minus t squared over 2. These are evaluated from 1 to 5. So you should get here, interestingly enough, 177 over 6, approximately 29.5 meters. So it's similar, but not exactly. The total distance always a positive number. So next problem, number 7. We just have to evaluate a definite integral from, it's actually indefinite. Indefinite integral x plus 2 over square root of x squared plus 4x. So we're going to review the technique called substitution. This integral does not remind you of any formula you've studied, so we have to use a substitution, and we're going to substitute u to be x squared plus 4x, because that's under the square root. Du dx is 2x plus 4. So we need to solve for dx, and that is du over, let me factor the 2 out. So this is the substitution we're going to do. Our integral becomes, I'll keep x plus 2 here, and here square the u, but instead of dx, I'm going to write du over 2 times x plus 2. And you can see this x plus 2 with this x plus 2 cancels, and I have integral du over 2 square root of u. I could factor out 1/2 and write this u to the negative 1/2 du, and our power function here can be integrated easily. So we have u to the negative 1/2 plus 1 is 1/2 divided by 1/2, and we cancel these 2's. So what's left, actually very simple, square root of u, or u to the 1/2. But you have to go back what u was right here. U was x squared plus 4x. And add a c at the end. So this is our indefinite integral. You get a function or a family of functions. Number 8. Now, we're going to have a definite integral from 0 to 3, absolute value x squared minus 4 dx. Another absolute value integral, so it will be helpful to review the function here, which we can break down to x minus 2x plus 2. And our interval is from 0 to 3. Where does this function become 0? We can write this down here. X minus 2 equals 0, so x equals 2, x plus 2 equals 0, x equals negative 2. So these are the two x-intercepts, or where the function is 0, but the one we're interested in the interval, so 2 right here. So we don't care about the negative 2 because it's outside our interval. So determine the sign. If the number is from 0 to 2, let's pick a number 1, plug it in, plug in 1 here, negative, positive, so that's negative. Pick a number from 2 to 3, 2.5, plug it in, and you get positive. So go back to our integral. Now instead of 0 to 3, it's going to be 0 to 2, and here our integral is negative. So I'm putting negative sign in front of it, dropping the absolute value, and then from 2 to 3 will be just x squared minus 4 dx. Okay, so this you can evaluate. You should get 23 over 3. All right, number 9. Number 9, we have another indefinite integral, and that is integral sine pi t cosine pi t dt, and I'm going to show you two methods. So let's right here, method 1. So in this method, I'm going to use a substitute and say pi t equals u. Du would be pi times dt, and dt is du over pi. So let's substitute and see what happens with our integral. So we're going to have integral sine of u, and then cosine u, and dt was du over pi. Pi is a constant, so I can pull it out. 1 over pi, integral sine of u, cosine of u. That to remind you of a formula from trigonometry, that is sine of 2x is 2 sine x cosine x. It's not exactly the formula because I'm missing a 2. But if I multiply by 2 and divide by 2, like this, then I'll have exactly the formula. And that becomes sine of 2u. All right, du. So now we're almost ready to integrate, except I have 2u here and u here. So you can do another substitution if you want to, where 2u is equal to, what do we want to use? Did we have x? No, we didn't have x, so let's just do x. So dx, let's see. So I wanted to do actually x equals 2u, it's the same thing. So dx is equal to du, and du is dx over 2. It's a very simple substitution, just a constant. So let's go back and finish the integral. I have sine of x instead of du, dx over 2. So the 2 goes on the front, integral sine of x dx. So that is negative cosine x. Okay, plus c, of course. And finally, we need to go back to our old variables. So first, we're going to substitute x with 2u, and that's negative 1 over So x was 2u. Just make sure. Negative 1 over 4 times 2, 8u. And then cosine of 2u plus c. And now we have to go back to what u was. And u was pi t. Pi t cosine of 2 pi t plus c. Okay. So I'm not sure how I got the 8. I think it should be 4. So, oh, I see. For some reason I had 4 here instead of 2. I don't know why this is 4 here. It should be 2. So let's fix this. So this is not 4. All right. So, no, there was 4 because dx over 2. That is 4. Okay, the second method involves a different substitution. So we have integral of sine pi t cosine pi t dt. But the substitution here is going to be u equals sine pi t. That may be easier. So du is equal to pi cosine pi t dt. And dt is du over pi cosine pi t. So we have this. And substitute now. So we have integral of u. I'm going to keep cosine pi t here. And instead of dt, I'm going to have du over pi cosine pi t. So now you can see the cosine pi t will cancel. And we have 1 over pi, which is a constant, integral of u du. And that is 1 over pi u squared over 2 plus c, 1 over 2 pi, and u was sine pi t squared plus c. So as you can see, our answer looks a little different than the one we had here, but it's not a problem because that constant c here is different. I'll call it c1. And so these two answers differ by a constant. There is a sine squared formula that you can write in terms of cosine to double angle. And that concludes the review.